Hello everyone. Today we will going to study about the topic ionic equilibrium in detail. This is part 2. Let's start. Disclaimer which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the images. This is our index slides and these are the major topics which we will going to see and which we will going to study today in detail. First, relation between acid and base dissociation, pH scale, hydrolysis of salts, solubility of sparingly soluble salts, solubility product, common ion effect, buffer solution, Henderson's equation for buffer solution, and buffer capacity. Let's start with our first topic, relation between acid and base dissociation. Relation between acid dissociation Ka and base dissociation Kb constants is Ka times Kb is equals to Kw. So this is the relationship between the acid dissociation constant Ka and base dissociation constant Kb, where pKa is equals to minus log Ka, pKb is equals to minus log Kb, and pKw is equals to minus log Kw. Many acids are capable of furnishing more than one protons in water. Such acids are called polybasic or polyprotic acids. For example, H2SO4, H3PO4, etc. So there are many acids which can donate, which can give more than one proton when it is dissolving in the water. And these acids are known as polybasic or polyprotic acids. The first ionization constant Ka1 is always greater than the second ionization constant Ka2. So if we compare the ionization constant, as we are talking about a polyprotic acid, so the two ionization constant will come, right? When first ions or first hydrogen ion is removing or dissociating, then first ionization constant Ka1, and then when second proton is donating or dissociating, then second ionization constant Ka2 will come. So the first ionization constant Ka1 is always greater than the second ionization constant, that is Ka2. Yeah. So let's study about the pH scale. It is used to express and compare acidic and basic strength of a solution. So if we want to find out our solution is acidic or a basic or what is its strength, we can do it by using pH scale. pH is defined as negative logarithm of H3O positive ion concentration or H positive concentration in moles per liter present in it. Thus we can write that pH is equals to minus log H3O positive concentration, or POH is equals to minus log OH minus concentration. And the sum of pH and POH is equal to 14. This is important. Okay. So relationship between pKa and pKb is given as. So pKa plus pKb is equals to 14, which is equals to pKw. pH scale range is 0 to 14 and it depends upon the value of Kw. So pH scale is measured the strength of acid or base from the range of 0 to 14 and it depends upon the value of Kw. As temperature increases, the value of pH decreases at 25 degrees Celsius or room temperature. Following observations are seen with the solution. First, pH of very dilute equivalent to 10 to the power minus 8 molar or lower acids or bases is nearly 7 but not 7. So pH of very dilute acids or bases is nearly 7 but not 7. That is not simply minus log acid or base concentration. Why? Due to ionization of water. Second observation, the pH of strong acid where the concentration is greater than 1 molar is never negative. It is 0 only. So if we have a strong acid with a concentration of greater than 1 molar, the pH of that acid is never negative. It is 0 only, because the range of pH is also only from the 0 to 14, right? So it can't go to the negative side. It can only be 0. If the acid is so much strong, then the pH can only be 0. It will not go in the negative term. There is a note: greater the value of Ka or Kb, smaller is the value of pKa and pKb, and stronger is acid or base. Okay, so this is the note that the Ka and Kb value is inversely related to pKa and pKb of an acid and a base. Okay, and the smaller the value of pK and pKb, the stronger the acid and the base. Or you can say the greater the value of K and Kb, the stronger the acid and base. Okay. So pH of mixtures of acids and bases. The rules for determining the pH of mixture of acid and bases are as follows. First, if strong acids or strong base remains unused, calculate the concentration or molarity of H positive ions and OH minus ions left in the solution, and then calculate pH or pOH accordingly. Okay, so if the strong acid or strong base remains unused, first we have to find out the concentration or molarity of H positive ions or OH minus ions left in the solution, and then we have to calculate the pH or pOH accordingly. Second, if weak acid or weak base is left behind or remains unused, a buffer, acidic or basic, is formed. Okay, so in the case of strong acid and strong base we have seen, but in case of weak acid or weak base, if it is left behind or remain unused, a buffer is formed. Calculate the concentration of salt formed, millimoles of salt formed per volume of solution, basically that is concentration, and the concentration of weak acid or weak base left behind. So we have to calculate the concentration of two things. First, the salt formed, and the concentration of weak acid or the weak base left behind in the solution, and use the buffer equation to calculate the pH of the solution. Okay, this is a way through which we can use the concentrations of salt and weak acid and weak base in case of weak acid or weak base left behind, and we can calculate the pH of that particular solution. Third rule is, if acids or bases are completely neutralized, then salt is formed. Okay, so if acid and bases are present and they completely neutralized, then salt is formed. Calculate the concentration of salt formed and use the hydrolysis equation to calculate the pH of the solution. So the two rules is for the one is for the strong acid and strong base left behind. Then second one is for the weak acid and weak base left behind. Third rule is for the acid or base that is completely neutralized, not the left behind or remain unused. Then the salt is formed. Then we have to calculate the concentration of that salt formed and use the hydrolysis equation to calculate the pH of the solution. pH value of a solution decreases on heating because ionization of water is an endothermic process. And in an endothermic process, if we heat if we give heat, if we supply heat, the del H will be negative. So in this case also, that pH value of the solution decreases on heating because ionization of water is an endothermic process. pH of boiling water is 6.5, 6 to 6, although it is neutral, right? When pH decreases by 1 unit, H positive ion concentration increases by a factor of 10. Similarly, when pH decreases by 2 units, H positive ion concentration increases by a factor of 100. Okay, so these are the 2 points which we have to remain in our mind. Keep in our mind that first one is for the value of a pH in a solution, whether how it will change on increasing the heat or decreasing the heat, on the supply of heat or not. And the pH of boiling water is 6.5, although it is neutral. And the second point is that pH decreased by, if pH decreased by 1 unit, that means H positive ion concentration in the solution increases by a factor of 10. And similarly, if pH decreased by 2 units, that means H positive ion concentration increases by a factor of 100. Okay, so what is hydrolysis of salts and what is the process? So the process of salt hydrolysis is actually the reverse process of neutralization. So whatever the thing is happening in the neutralization process, the salt hydrolysis process is the reverse of this. The reaction of an anion or cation of salt with water accompanied to produce acidic and basic solution is called salt hydrolysis. Salt hydrolysis affects the pH of the solution. If the salt hydrolysis process is happening in a solution, then its pH will definitely going to affect. Salts of strong acid and strong bases, that is neutral salts, do not undergo hydrolysis, are called neutral salt. For example, NaCl, calcium sulfate. If such salt is dissolved in water, the pH of the solution remains 7. Okay, because they are neutral salt. Salt of strong acid and weak base, for example NH4Cl, are called acidic salts. Such salts undergo cationic hydrolysis, and the pH of acidic salt solution will be less than 7 because the salt will be acidic salt. So pH will be less than 7. For such salts, H3O positive concentration is equals to under root KH times concentration, and KH, which is the hydrolysis constant, is equals to Kw upon Kb, or you can write pH is equals to 7 minus half of pKa plus log C at room temperature. And Kb here is ionization constant for weak base, B is for base, and C is molar concentration of the salt. So this is about the process of hydrolysis of salts. Now, the salt of strong base and weak acid, for example NaNO2, NaCN, CH3CONa. So here who is dominating? Base is dominating. Strong base and weak acid. So the salt will be basic salts. Such salts undergo anionic hydrolysis, and the pH of basic salt solution will be more than 7 because the salt is basic salt. So for the bases, the pH will be more than 7. So the pH of that salt solution with basic salt will be more than 7. For basic salts, OH minus is equals to under root KH times C, or KH is equals to Kw upon Ka. pH can also be written as 7 plus half of pKa plus log C at 25 degrees Celsius. The salts other than halides, sulfates, nitrates of metals fall into salts of weak acid and base category. For example, CH3COO, NH4, etc. And for such salts, KH is equals to Kw upon Ka times Kb, and pH is equals to 7 plus half of pKa minus pKb. There is a note, there is no effect of dilution on the hydrolysis of salts of weak acid and weak base because pH and KH are all independent of concentration. So this is a note, this is a point to remember, that pH and KH are independent of concentration. Okay, and that's why there is no effect of dilution on the hydrolysis of salts of weak acid and weak bases. Yeah, so solubility of sparingly soluble salts. Lattice enthalpy and solvation enthalpy play an important role in dividing the solubility of the salts in particular solvent. These are two terms, lattice enthalpy and solvation enthalpy. They are the important they play important role in dividing the solubility of salts in the particular solvent. For a salt to be able to dissolve in a particular solvent, the solvation enthalpy must be higher than its lesser enthalpy. So how they are related? So if we want a salt to be able to dissolve in a solution, in a particular solvent to make a solution, the solvation enthalpy must be higher than its lattice enthalpy. That's the relation between these two terms. So if we want a salt to be dissolved, the solvation enthalpy must be higher than lattice enthalpy. Right? And okay, let's see about the solubility product. So the solubility product defined as product of molar concentration of its ions in a saturated solution. Each concentration terms raised to the power equal to the number of ions produced on dissociation of one molecule of electrolyte. For example, we have a molecule AXPY. X and Y are the numbers of atoms of A and B. How it will dissociate? It will dissociate into X of A positive plus Y of B negative. Right? Now, KSP for this reaction will be A positive whole power X, B negative concentration whole power Y, because X and Y are the stoichiometric coefficients of A and B respectively. Now let's take an example, A2X3. So X is 2 here, Y is 3 here. So it will dissociate into 2 times A3 positive plus 3 times X2 negative. Okay. Now let's suppose the solubility will be 2s for this 2a3 positive and 3s for this 3x2 negative, because let's suppose A2X3 has S solubility. Then the KSP will be A3 positive concentration whole square, X2 negative concentration whole thrice. In the terms of solubility, A3 positive whole square will be 2s whole square and X2 negative 3 whole cube will be 3s whole cube. And on solving this, we have KSP value for this is coming out as 108 s to the power 5. 3 plus 2 will be 5. Right? So through this manner and in this way, in this process, we can find out the KSP or solubility product of any reaction for any dissociation reaction. Okay? Yeah. Now, let's suppose this is a reaction B of BaSO4. It is going in a saturated solution in water and giving us Ba2 positive plus SO4 2 negative, right, in the aqueous solution. Let's suppose the solubility of Ba2 positive is S and SO4 2 negative is also S. Now KSP will be Ba2 positive concentration multiplied by SO4 2 minus concentration. And we have a solubility of Ba2 positive. So let's suppose, let's put it in the place of Ba2 positive. It will be S times S, because S is also the solubility for the SO4 2 negative. So KSP is coming out as S times S means S square, right? S is molar solubility and KSP is solubility product. This is important. So this is the way, this is the example that how can we calculate the KSP, the solubility product for a reaction going under dissociation, right? There is a note here that if the ionic product exceeds the value of solubility product of a sparingly soluble salt, then precipitation will occur. Okay, so if we have an ionic product and we have a solubility product, okay, so and the ionic product exceeding the value of solubility product, that means solubility product is lesser than the ionic product value of a sparingly soluble salt, then the precipitation will start occurring for that particular solution. Okay, yeah. Now let's see about the common ion effect concept. So it states that if to the solution of a weak electrolyte, a solution of strong electrolyte is added. So if we add strong electrolyte solution in a weak electrolyte solution, which furnishes an ion common to that furnished by the weak electrolyte. Okay, the ionization of weak electrolytes is suppressed. Basically, what we are saying that we are adding a solution of strong electrolyte into the weak electrolyte, and the strong electrolyte which is added is furnishing an ion common to the furnished by the to the ion furnished by the weak electrolyte, right? So what will happen? The ionization of weak electrolyte is suppressed. For example, in the case of NH4OH, it dissociates into NH4 positive plus OH negative. So if NH4Cl or NaOH, because in NaOH, OH minus is ion common to the NH4OH, and in NH4Cl, NH4 positive is the ion common to the NH4OH. If these two compounds is added to the NH4OH solution, the above equilibrium will shift to the left due to high concentration of common ion, and therefore the ionization of NH4OH, which is initially here, is further suppressed. Okay. In the second group of qualitative analysis, H2S is passed in the presence of HCl. This is due to the fact that HCl suppresses the ionization of weakly dissociated H2S. Okay, so we use this fact of common ion effect here in the case of H2S and HCl. Due to this, only sulfides of second group radicals are precipitated, and sulfides of third and fourth ETC groups are not precipitated because of their high solubility product. The common ion effect is also used for almost complete precipitation of a particular ion, as it's a sparingly soluble salt with very low value of solubility product for gravimetric estimation. This is important and point to be noted. Yeah, so let's see about the buffer solution. So what is buffer solution? The solution which maintains its pH constant or reserve acidic or basic nature even upon addition of small amounts of acid or base is called buffer solution. You can, in easy language, you can say that a solution in which both acid and base is present, but still its pH is neutral, and the pH remains constant even if we add the small amount of acid or base. That type of solution is known as buffer solution. The ability of buffer solution to resist changes in the pH on addition of acid or base is called buffer action. And this ability of the buffer solution, that it resists the changes in the pH remains constant in the buffer solution. This ability, on addition of acid or base, the resist of changes in pH of a buffer solution, this ability is known as buffer action. A buffer solution should exhibit following characteristics. First one, buffer solution possesses a definite pH value. Okay, so basically, as we are saying that buffer solution is having a constant pH, that means it should possess a definite pH value. Second, their pH value remains constant on keeping long or dilution. On dilution, on keeping long the solution, the pH value of the solution remain constant. Third, the pH value is not changed on the addition of strong acid in acidic buffer and a strong base in basic buffer. Buffers are also of two types, like acidic or a basic. So the pH value is not changed on the addition of strong acid in acidic buffer and strong base in basic buffer. So basically there are two types of buffer, as I said, are as follows. First one, a buffer solution pH of which is less than 7 is called acidic buffer. Weak acid with its salt of strong base gives acidic buffer. So weak acids, the acids which are weaker in nature with its salt of strong base, but the base is strong, gives the acidic buffer. For example, this is a weak acid, CH3COH acetic acid plus CH3COONA and HCN plus NaCN. These are the two pairs of buffer solution which is acidic buffer. Okay, and they are having pH of less than 7. Okay, And in this, the weak acid is present, and the weak acid is present with the salt of strong base. Like you can see CH3CONA, it is a salt of strong base NaOH. So, and HCN plus NaCN is also a pair of acidic buffer. So, second type of buffer solution is a basic buffer, and it has is this solution or this buffer solution having pH more than 7, and it is called basic buffer. So, weak base, it is just opposite of acidic buffer, right? So, weak base with its salt of strong acid gives basic buffer. For example, this pair NH4OH plus NH4Cl, like weak base is NH4OH plus strong acid salt. NH4Cl is a salt of HCl, which is a strong acid. So this pair is basic buffer. Similarly, C6H5NH2 plus C6H5NH3 positive Cl negative. This is a pair of basic buffer. So these are two types of buffers, acidic buffer and basic buffer. And of course, the pH of these two buffers will depend upon the acidic nature and basic nature. So acidic buffer will have the pH less than 7, and the basic buffer which will have the pH more than 7, right? As per the acid buffers, as per the acid nature and the base nature. Okay. Now, Henderson's equation for buffer solution. For acidic buffer, pH is equals to pKa plus log of salt concentration divided by acid concentration for acidic buffer. And for basic buffer, the pOH is equals to pKb plus log of salt upon base concentration. Okay, so these are the two equations given by Henderson's for the buffer solution. For acidic buffer, it is in the terms of pH and pKa and acid concentration, and for basic buffer, it is in the terms of pOH, pKb and the base concentration. Okay, so these are the two equations given by the Henderson's, known as Henderson's equation for buffer solution, acidic and basic buffer. Okay, now what is buffer capacity? So a buffer capacity is quantitatively defined as number of moles of acids or base added to 1 liter in of buffer solution to change the pH by unity. So basically, buffer capacity is quantitatively defined. We are talking about quantitatively. So buffer capacity is quantitatively defined as number of moles of acids or base added to 1 liter of buffer solution uh, to change the pH by unity, by 1. Unity means 1. So buffer capacity is equals to number of moles of acid or base added to 1 liter of buffer divided by the change in the pH. Buffer capacity is maximum when the concentration of salt is equals to concentration of acid and pH is equals to pKa for acidic buffer. Similarly, buffer capacity is maximum when salt concentration is equal to base concentration and the pH is equals to pKb for basic buffer. So for these two buffers, acidic and basic, the condition for the buffer capacity to be maximum is this stated here, that salt concentration should be equal to acid concentration and pH should be equal to pKa for acidic buffer, and the salt concentration is equals to base concentration, pH is equals to pKb for the basic buffer. Now, greater the buffer capacity, larger is its capacity to resist the change in the pH value. That is like buffer capacity, right? Because a buffer solution is a solution which resists the change of the pH. It maintains the pH at a constant value, whether we are adding a small amount of acid or a base in it. So the buffer capacity, that means greater the buffer capacity, larger is its capacity, its ability to resist the change in the pH value of the solution, of the buffer solution. Okay, that is the buffer capacity. And in the quantitative term, we have defined it here that buffer capacity is equals to number of moles of acid or base added to 1 liter of buffer divided by what is the change in the pH. Okay, this is the formula. Okay, we are at our summary slides. So These are the major concepts which we have covered today, and let's go through by them one by one. Acids dissociate in water to produce hydrogen ions, while bases dissociate to produce hydroxide ions. Strong acid or bases dissociate completely, while weak acid or bases only partially dissociate. This is the difference between strong acid or strong base, or weak acid or weak base, right? The pH scale measures acidity or basicity of a solution ranging from 0 to 14. When salts dissolve in water, they can hydrolyze to form acidic or basic solutions. The nature of ions produced determines whether the solution is acidic, basic, or neutral. And the ions produced from the parent acid or base. Okay, so the solubility product constant Ksp quantifies the solubility of the salt. So solubility product constant defined or tell us that what is the solubility of that particular salt. The presence of a common ion decreases the solubility of a sparingly soluble salt. We have studied this, right? That if the common ion is present, then it decreases the solubility of sparingly soluble salt. A buffer solution resists change in pH when small amount of acid or base are added. Henderson-Hasselbalch equation for buffer solution relates the pH of a buffer solution to the concentration of acid and its conjugate base. We have seen this in the equations of Henderson's. Lastly, the buffer capacity is a measure of the ability of a buffer solution to resist the change or any kind of change in the pH of the buffer solution. So these are some major concepts which we have covered in this lecture. Okay. Thank you.